problems the world faces, engineers face, are multidisciplinary in nature. They require a multidisciplinary systems approach to solve. How does an engineer solve these problems? Well, most solutions don't start with a blank sheet of paper. Most solutions start with something that exists that we improve either with new technology or new knowledge. Or a solution may result from the combination or integration of two existing systems in some innovative way. In order for that to happen, engineers must understand completely, thoroughly, how a system works. In addition, when engineers are engaged in the design process, they don't want to develop concepts, candidate solutions to a problem, and then design, build, and test each one. It's too costly, too time-consuming, does not result in understanding, will not result in innovation. How then does an engineer in the design process evaluate concepts without building and testing each one? Well, the key to all of this, the most important aspect of modern engineering is modeling. And modeling is an essential element in a process engineers use to understand existing systems and also to evaluate the concepts they generate in the design process. And that process is called the engineering system investigation process. Let me describe this process to you. And let me do that by applying it to a mechanical system. Why a mechanical system? Most of the products, devices, systems that we have in our home, at the workplace, in transportation, involve mechanical systems, mechanical structure, and mechanical motion. Now, the simplest dynamic mechanical system one can build is the system I have right here with me. It's a spring mass system. Now, these mechanical systems that are parts of almost everything we experience day to day have three essential attributes: mass or inertia, springiness or compliance, energy dissipation or friction. Now, these attributes may be difficult to identify in a particular mechanical system, or they may be very, very easy and clear to identify. And this will become obvious as we apply this process to this simple, dynamic, mechanical, physical system. Let me describe the physical system to you. This is called a spring mass system. It's a physical system. It's real. I can touch it. It consists of some support structure that's mounted on this table. To one point on the support structure, I attach a spring, a real spring. It's like a spring in your garage door. The spring has mass. It has springiness. That's why it's called a spring. It also will dissipate energy upon cycling. It also has pretension. The coils are pulled together and require a certain amount of force be applied at the ends of the spring before the spring starts to stretch. The spring is also a tension spring. It doesn't compress. It's attached to one end, by one end to the support structure, and by the other end to a mass. A mass that will translate up and down. This mass is a block. It's a tray in which I have masses that I can add or take away. It's rigid. Nothing is really rigid, but we'll consider it to be a rigid mass. Now, this mass is constrained to translate up and down. Why? Well, we have attached to the structure a linear bearing. Linear meaning translational as opposed to rotary. One part of it is attached to the structure, the other part is attached to the mass, which will translate up and down. This is the system, the physical system. If I displace this mass by pulling it down, stretching the spring and releasing it, you see it oscillates up and down. The amplitude of the oscillations decay over time, and eventually the mass stops moving. This is the physical system, And it's the first step in this investigation process is to understand the physical system, the system that exists physically. But remember, this could be a concept in the design process. And so right now it's just a sketch, a schematic of some concept. We need to understand this system by applying this investigation process, and the first step is what we call physical modeling. Well, what is a model? Is it a fashion model? Well, certainly not. Is it a model airplane? No. Is it something we build? No. Is it a rapid prototype model or a CAD model? No. It's a simplification, an idealization of this physical system based on engineering judgment and engineering simplifying assumptions. It's the most difficult part of the entire process because it depends on an engineering experience. So we develop a physical model of this physical system, and this model is an idealization, and it can take many, many forms. And it always in response to the question, why am I modeling? And there are many reasons why engineers model. Initially, we model to get insight into the behavior of a physical system or a concept in the design process. As we proceed with our development, we model to make sure that when we finally build the system and turn the power on, it's safe. It operates as we expect. No surprises, right? No breakdowns, no danger. So there's a whole hierarchy of physical models possible, from the very simple for design insight, which is less real, less complex, more easily manageable analytically, to the truth model that we use before we actually build and implement, turn the power on, which is more real, more complex, less easily solved analytically, less easily managed analytically, but certainly more real and a more accurate predictor of the actual behavior of the system. So what simplifying assumptions might I make for this dynamic physical system? Well, let's start. The structure mounted on this table, I'll assume, is a rigid structure. Nothing, of course, is rigid, but I will assume that, which essentially says that the environment, the surroundings, are independent of any system motions. Well, as I move this, the structure may wiggle and wobble and the table may shake, but I'm neglecting that. The spring. We describe what the spring is physically. The spring has the name spring because its main attribute is springiness. So I'm going to assume that this spring is what we call a pure spring. Now, a pure spring is fictitious. It doesn't exist, but it's an essential building block in physical modeling, in this case, modeling mechanical systems. A pure spring has springiness and nothing else. No mass, no energy dissipation. It's not real, but it's a building block that I can use to capture that attribute of compliance, springiness in the mechanical system. So the spring is a pure spring. And indeed, it's also a tension spring that doesn't compress, and there's a certain amount of pretension in that spring as we described. So I'll treat the spring as being pure. I'll also treat the spring as being linear. Now, this is not linear in the sense that the bearing is linear, which means translational motion. Linear in the sense that when I take a spring and I apply a force to the ends, over the range of motion that I'm interested in, I assume that the relationship between the applied force at the ends and the displacement of that spring, the stretch of the spring, is linear, straight line. It can be described by a graph that is a straight line. That's what we mean by linear. And when something is linear in behavior, we call it ideal. So I model this as a pure and ideal spring. Now, the spring has mass. What gives me the right to neglect the mass of the spring? What gives me the right to neglect the damping, the energy dissipation in the cycling action of the spring? Well, we neglect aspects of a physical system when they are small relative to something else. So when the mass of this spring is less than 10% of the mass I attach to it, from experience I know it makes sense for me to neglect that mass. And when there are other energy dissipating mechanisms in the system that are much greater in effect than the energy dissipation in the cycling of the spring, I can neglect that friction loss in the spring. So that gives me the right then to say that this is a pure spring. And if I restrict the motion to that linear range where force is proportional to spring stretch, then I treat it as an ideal spring. Moving down to the mass, again, I treat it as being rigid. It's a tray of aluminum with steel blocks that I can add or remove. Because it's a rigid mass and it's constrained to move up and down, I can treat it as a point mass. It doesn't rotate, it doesn't move out of plane. It translates up and down in 1 degree of freedom motion. What constrains it for that motion? The linear bearing, the translational bearing, which consists of balls and a track with oil, again, allow it to just move up and down. Constrain it to move just up and down. So this is a point mass in 1 degree of freedom motion. What about this linear bearing? The linear bearing is a constraint. I added it. Why? So I would have 1 degree of freedom motion. I did not add it to add friction to the system. That is what we call a parasitic effect. But this parasitic effect, unwanted effect, is great. It's the primary reason these oscillations eventually decrease in amplitude and the motion stops. It's not because of the energy dissipation in the spring. It's not because of the effect of the air that surrounds this. It's because of the friction in that bearing. That's what dominates the energy dissipation characteristics of this system. That friction is rather complicated. And so how do I then capture the effect of that energy dissipation? Well, I could go in and I could try to analyze that bearing. There's probably some mathematical expressions for the friction in a linear bearing due to the rolling and sliding of the balls with an oil of a certain viscosity. Do I trust that? Probably not. It would give me maybe an order of magnitude value for the friction. I could go and test that bearing offline and see what the friction is. Or I could look at experimental results from other researchers. Or look at a handbook. Look at some experimental data from the manufacturer. But somehow I have to capture what this friction is in my system. What the friction is predominantly in this linear bearing. I'll need to make that assumption, and we will talk about that. Another assumption is that gravity acts straight down and is constant for my location here in this laboratory. Also, I assume that any of the physical parameters of this system, the mass, the spring constant, the energy dissipating characteristics, however I quantify them, don't change with time, don't change with temperature. Do they? Well, of course they do. But for the duration that I'm speaking about and I'm considering, they don't. These are the simplifying assumptions that then lead me to the physical model. So after I understand the physical system and its structure, how it was created, because after all, I built it. I'm responsible for it. I put it together this way. I must understand it. I understand it by making simplifying assumptions using engineering judgment and creating an approximation, a physical model, which I will then sketch, represent on the whiteboard. Let me show you what that is. Let me first bring this cart closer to me. Stop. So my physical model starts with what I would call ground. Ground simply means that which doesn't move. And I show it as indicated. The mass, the rigid mass, I show with just a block. And I show its mass with a capital M. Now I know this mass is connected to ground through a spring, and I will represent the spring by what you know to be a spring element, a squiggle line, which looks like a spring and represents a spring. Now remember, this is a pure and ideal spring. And we'll talk about how we identify its attributes in a minute. Now there's also friction in this system. And there's a frictional force acting on this translating mass. This mass moves up and down, and it's constrained to move up and down, again, by that linear bearing. And I'll show that constraint by just showing sidewalls. This moves up and down, and I'll show the direction for gravity acting down, and I'll say that this is my plus x direction. 1 degree of freedom motion. Now, to represent the energy dissipation, the frictional force acting on this mass, I'm going to show 2 lines with a big question mark in the middle, because I don't know what that is. Physically, it's a combination of many effects. Air damping, material damping in the spring, some sort of fluid damping in the translational linear bearing, some sort of Coulomb dry friction damping due to sliding of the balls in the track. It's a very complicated combination. How do I capture this physical effect? Well, again, how much detail do I need to understand the behavior of this system? At this point, I'm looking for insight into the behavior of the system. So typically, engineers will use a very simple approximation to friction that lends itself to easier analysis. And that approximation is what we call a viscous damper. We all have experience with a piston moving in a cylinder with perhaps holes or a small space through which fluid can travel. The shearing action of that fluid between the piston and the cylinder is what creates the frictional force. And that frictional force is proportional to the velocity of the moving mass. So what I will represent here then, in place of the question mark, is what we call a viscous damper. So I'm going to replace that question mark with what looks like a piston in a cylinder. And this piston in a cylinder then represents an approximation to this cumulative effect. Do I need to understand that cumulative effect? Most definitely, if I ever want to improve this system or use it as part of a larger system. But for now, my purpose is insight. Remember, we model in response to the question, why am I modeling? So I'm using a simple element, and again, this is also a pure and ideal element, because a piston in a cylinder has mass. It has springiness. But I really don't care about that. I care about its energy dissipating capacity, its characteristic. And so this is also a pure and ideal element because in addition to being pure, only have friction, I also assume that it's linear in behavior and that the force applied to it is proportional to the velocity of its ends. Linear, just like the spring. So this then represents my physical model based on simplifying assumptions, judgment, experience applied to my dynamic, physical, mechanical system. Part of this physical modeling is assigning parameters to each of the elements in my model. What kind of parameters does the spring have? Well, if I were to take this spring with the mass attached and perhaps remove a weight or two, I could then, if I were to take this entire mass off, I could measure the unstretched length of the spring. So that's something I need to know. What is the unstretched length of the spring? We'll call that L sub 0. Once I add a mass, and here the tray, which is rather light, it's aluminum, but add a steel mass and another steel mass, and you see the spring stretches, I could plot on a horizontal and vertical axis, on horizontal displacement from that unstretched length of the spring, and the force, which is the weight applied to that spring, I could plot that point. And maybe there it is. If I add another mass, the spring stretches a little more, the force is a little greater, and maybe I have another point. And I could do this over the range of motion that I'm interested in. I could then draw a straight line. Now, this straight line might extend beyond that last point, but it certainly can extend past this point here, which represents the unstretched length of the spring, because the spring is a tension spring that doesn't compress. So we're not allowed to apply a negative force because the coils will bang together. And that's not the range of motion that I'm considering. I'm considering a range of motion where the spring is always in tension, it oscillates up and down, and the spring is not stretched too much to the point where perhaps this curve is no longer straight, but maybe bends up, or maybe bends down. In one case, the spring gets stiffer. In the other case, the spring gets softer. But I'm not interested in that motion. I'm interested in this range of motion. Now, the slope of this line we call K, the spring constant, and the intersection of this curve with the force axis we call F sub t, which is the pretension in my spring. So we see there are really four parameters: L0, K, F sub t, and of course, the mass of the spring. And we're neglecting that, but it still needs to be determined, so we can then say it is less than 10% of the mass I attach to it. So of these parameters, K is certainly important, and the pretension F sub t is important for our analysis that will follow. Over here, for this viscous damper, again, if I were to draw a graph of force versus velocity, this pure and ideal element would have a slope that looks like that. Now, I don't have anything to test here. I'm assuming I'm trying to capture the physical nature of the energy dissipation in the system by this pure and ideal element. And again, this is an assumption. How good is the assumption? I don't know yet, but I must know, and we will. The slope is B. That's called the viscous damping coefficient, and I assign it to that element. Here I did an experiment because I have the hardware. Here I didn't do an experiment because I don't have that element. I'm trying to capture the essential features with this pure and ideal element that behaves this way. What else do I need to know? I've assigned all the parameters that I need: gravity, the mass that's attached. This then represents my physical model with the parameters. You see that I can identify K and the pretension. I can find L0 and the mass of the spring and the mass attached. How do I find B? This is part of this element that I'm trying to use to represent a cumulative effect. It's a challenge. It's a good question. We'll see how we might do that. This then represents the physical model with the parameters and numerical values of those parameters I need then to go to the next step in the process. What's the next step? The next step in the process is what we call mathematical modeling. Now, this is very, very important. There are two types of models: a physical model, which we've created by assumptions, judgment, experience. Next, I apply the laws of nature, whatever laws I think are relevant, not to the physical system, but to the physical model. What law of nature? Well, I apply Newton's second law. Newton's second law says that the summation of forces equals mass times acceleration. These are forces that are applied externally to the system. What system? Well, in order to apply this, I need to identify what I'm applying it to. In this case, the system consists of my block of mass m. And there are many, many forces acting on that block. And this diagram that I'm drawing here is what we call a free body diagram. It's a diagram of this mass, which I remove from its environment and draw on the board and show the forces acting on it by contact or at a distance, but all of the external forces. The only force that acts at a distance is gravity. There are no electromagnetic forces here. And so that is its weight, which is its mass times its acceleration due to gravity. Again, this is the plus x direction. And gravity is acting straight down. What other forces are acting? Well, certainly the spring force, because the spring is connected to the mass. And that force acts up if I move the mass in this plus x direction, because the spring is in tension. And from my diagram, that force is equal to the pretension plus the spring constant times the displacement from that unstretched length of the spring. Now, we know, because we observe that these oscillations decay, there must be some frictional force acting on this mass. I must capture that effect. I've done so with a pure and ideal viscous damping element, an essential building block. Like the pure and ideal spring, this pure and ideal viscous damping element I will use to capture the frictional effects. That damping force opposes the velocity of the mass. So if the positive direction velocity is down, the friction force acts up, and it's proportional to that velocity. Well, B, what is it? Well, I still don't know. Because physically, I can't measure it. I'm using it to represent a cumulative effect. It's not real in my system. I'm using it to somehow capture that effect. So this is a challenge, and we'll talk about how we're going to do that. Well, my free body diagram is now complete. And now I apply Newton's second law, summation of forces equals mass times the absolute acceleration, the acceleration with respect to ground, to this free body diagram. And what will my equation then result? What will the resulting equation be? Let me show it. If positive is acting down, I have plus m times g minus the pretension force in the spring minus k times x minus b times v, and that all equals the mass times the acceleration. If I redraw this, rewrite this equation, I'll show it as mass times acceleration plus b times v plus kx plus the pretension equals m times g. Now this equation, it looks algebraic, but it's not. Why? Because velocity is the time derivative of displacement. Acceleration is the time derivative of velocity. So I recognize this equation as an ordinary differential equation, derivatives with respect to time. It's a linear ordinary differential equation. Because the equation is linear, I don't have derivatives, accelerations, or velocities squared, or the products of velocities with displacements. It has constant coefficients because we assume that. M, B, K, F sub t, G, constant. Don't change with time, don't change with temperature. I know how to solve this equation. I've taken math courses in differential equations. There's computer software that will solve this very easily. So solving this is not the challenge. But in order to solve this, I need numerical values of these parameters. I need m, I need k, I need f sub t, I need g, and I need b. Well, how can I estimate b? Well, One way to do it is as follows. In order to assess the validity of this model, what I need to do always is measurement, experiment. There's a saying in engineering that computer simulation, or modeling, analyzing, predicting, without experimental verification is at best questionable and at worst useless. So the investigation process, which started with the physical system, went to physical modeling, went to parameter identification, went to applying the laws of nature and developing a mathematical model, then went to solving this equation analytically, numerically, both, to get insight to predict the behavior of the system, is only half the story. The other half is measuring the behavior of the system to validate my model. In order to do that, I must have a sensor, a device that will experimentally give me information on the behavior of the system. I have mounted here an infrared optical position sensor for my mass, so that as this mass moves up and down, I will get a trace of position versus time. Now, if I displace this in the positive x direction and release it, that trace, if I were to sketch it here, would look like this. If this is time and this is displacement, then if I started it at some positive x displacement, it would move in the negative direction and oscillate. And it would oscillate within some envelope, which I'm just going to sketch here. Now, this is not part of the response. This is just an envelope within which these oscillations take place. I mean, how do I know there's an envelope here? Well, the oscillations decay, so there must be some symmetry to this, or I assume there's some symmetry to the response. Eventually, these will persist and decay and get smaller and smaller and eventually stop. Well, one way of determining this value of B would be to take this real response and by simply curve fitting, choosing some reasonable values for B and solving this equation and comparing it to the actual response, I could then determine an approximate value for B. It's one way of doing it. I could do some analysis, I could do some side testing, I could do some calculations, but in the end, whatever I predict has to be compared to what I measure. And based on that comparison, I take action. If the comparison is good, and if I choose B well, the comparison will be good. In which case, I can then say my modeling is successful, my prediction is valid, it's been verified, and I can now use this to predict how the system will behave if I make changes, improvements, or if I use this as a subsystem in some concept, as part of some larger multidisciplinary system. But the comparison between what we predict and what we measure is essential. If you don't do that, all of your modeling, analysis, prediction activities might be useless, might be dangerous, if you then suppose that you can then use this in an actual design. So, we've completed the investigation process. One word about this response. This response, as I've sketched it, is what this system gives me. This envelope that I've shown here, again, for different types of friction, it will take different forms. But the oscillation will be somewhat sinusoidal. It will have some frequency. The amplitudes will decay. And the B value would be selected to best match the prediction with the measurement. Once I have that agreement, my investigation is essentially over. I can then proceed with the rest of my design or with more detailed investigation if the answer to my question, why am I modeling, warrants that. Modeling is the key to modern engineering practice, and modeling is an essential element, physical and mathematical modeling, in the engineering system investigation process.